Today we will continue our discussion on reflection of plane waves from a dielectric to another dielectric interface and when the wave is incident at an oblique angle. Last class we derived equations for the transmission and reflection coefficient for parallel and perpendicular polarization in terms of the intrinsic impedances of the two media, medium 1 and medium 2, and also in terms of angles theta I and theta t. Theta I is the incident angle, theta r is of course equal to incident angle equal to theta I, and theta t is the transmission angle. Now we will see these equations little closely, taking some examples. Let's take the situation when the wave is incident from air onto a dielectric slab of permittivity, relative permittivity of 2. And what this picture shows is gamma parallel and tau parallel as a function of the incident angle theta I. So if you see the transmission coefficient, as theta I increases from 0 to 90 degrees, it monotonically decreases. Whereas the reflection coefficient is very interesting. First it decreases, touches a 0 at a particular angle, and then it starts increasing and goes to 1 when theta is equal to 90 degrees. So we have a particular direction. If the wave is incident from that direction corresponding to theta I, a particular value of theta I, where the reflection coefficient is 0. No wave is reflected back if the wave is incident onto a dielectric medium with permittivity 2 from air. Now, and this is the case when we have parallel polarization. Remember what is parallel polarization? The electric field is parallel to the plane of interface. Correct. Now we'll ask this question, can we plot a similar graph when epsilon r equal to 4? So this is the picture for epsilon r2 equal to 4, and of course medium 1 is still air. We still have a very similar behavior. If you notice, the reflection coefficient at theta I is equal to 0 is higher as compared to epsilon r2 equal to 2, but it will still has an angle when the reflection coefficient will be exactly equal to 0. That is, there is no reflection at all when the wave is incident at that particular angle, slightly more than 60 degrees, about 63 degrees or so. What happens when epsilon r2 equal to 6? When epsilon r2 equal to 6, we have a similar behavior once again. This time, the angle where the reflection coefficient becomes 0 is slightly more than the previous case. So, and the reflection coefficient at theta I equal to 0 has gone up. In summary, as the discontinuity increases, the reflection coefficient when wave is normally incident, which corresponds to theta I is equal to 0, the reflection coefficient increases as the discontinuity increases. And there is always an angle here which correspond, and if the wave is incident at that angle, the reflection coefficient will be 0. So the question that we are going to ask is it possible to find an equation for this angle so that we don't have to do numerical calculations? Straight away, given the material properties, we should be able to estimate the angle when the reflection coefficient goes to 0. That is the angle we are trying to, that's the angle for which we need an equation. Let's start with the expression for reflection coefficient. Gamma parallel is equal to eta 2 cosine theta t minus eta 1 cosine theta I upon eta 1 cosine theta I plus eta 2 cos theta t. This is the equation for the reflection coefficient, and we are going to ask the condition when will gamma parallel become 0. This will become 0 if we choose eta 2 cos theta t equal to eta 1 cosine theta I. Basically, the numerator of that equation for reflection coefficient, when it becomes 0, gamma parallel is 0. Therefore, we want to find a condition for this. This condition has to be satisfied. When this condition is satisfied, we can find an equivalent equation for the value of theta I. That's very easy. Let's square it up. and write eta 2 as square root of mu upon eta as square root of mu epsilon. Therefore, eta square is mu by epsilon, and we can write cos square as 1 minus sine square. This process is very standard. I mean, we keep using it more often. First time I'm going to write down all this. In the next slides, I'll just skip these equations. Now, once we have sine square theta I, sine square theta t, yes, we can use Snell's law, which is beta 1 sine theta I is equal to beta 2 sine theta t. Substitute in this, you get a little longish expression. Look at this beautiful one. We started off with a cute tiny eta 2 cos theta t equal to eta 1 cos theta I. We kept on expanding and it looks very awkward. Well, you just have to rearrange the terms. The beautiful part of this equation is we got rid of theta t. We know mu1, epsilon 1. We know mu2, epsilon 2. The only unknown in this equation is theta I. So we rearrange the terms. It becomes sine theta I is square root of mu2 by mu1 minus epsilon 2 by epsilon 1 upon epsilon 1 by epsilon 2 minus epsilon 2 by epsilon 1. Convince yourself that this equation is indeed correct. Given sine theta I, then so what did we find out? Gamma parallel equal to 0 corresponds to a particular value of theta I, which is given by sine inverse of that quantity under square root sine. This angle, when the reflection coefficient goes to 0, is known as Brewster's angle. This is the Brewster angle, usually represented as theta b. Therefore, sine theta b is equal to this quantity here. We take a very specific example when mu2 is equal to mu1 equal to 1 and there is no magnetic permeability, or the permeabilities are equal. This is also valid when mu2 is equal to mu naught and mu1 is equal to mu naught. That is, material has no magnetic permeability at all, purely dielectric material. Then sine theta b comes out to be a simpler equation in terms of epsilon 1 and epsilon 2, and just take the epsilon 1, take it to the numerator and then rearrange the terms and write epsilon 1 square minus epsilon 2 square as epsilon 1 minus epsilon 2 times epsilon 1 plus epsilon 2. Knock off epsilon 1 minus epsilon 2 from both numerator and denominator, and you are left with epsilon 2 upon epsilon 1 plus epsilon 2. Sine theta b is square root of this. Therefore, if I were to construct a right angle triangle with sides as root epsilon 1 and root epsilon 2 and hypotenuse as square root of epsilon 1 plus epsilon 2, then sine theta b is root of epsilon 2, that is opposite side, upon epsilon 1 plus epsilon 2. Therefore, tan theta b is much simpler, is root of epsilon 2 upon epsilon 1. This is the condition that gives us the angle when the reflection coefficient becomes 0. And that angle is known as Brewster angle. This is valid, this equation is valid when material permeabilities, the permeabilities of the two regions are equal. Now, continue with our example. When we had epsilon r2 equal to 4, we can calculate tan theta b as square root of 4, that is 2. Therefore, theta b is tan inverse of 2, which gives us 63.44 degrees. That's what happens if you see the graph here. The green trace goes to 0 at 63.44 degrees, which corresponds to Brewster angle. Now, we ask the same question. Can we see Brewster angle in perpendicular polarization? Gamma perpendicular is given by this equation. We ask the question, when will gamma perpendicular go to 0? When eta 2 cos theta I is equal to eta 1 cos theta t. And if you introduce the Snell's law, beta 1 sin theta I is equal to beta 2 sin theta t into this equation, exactly the same thing. Square it up, write cos square as 1 minus sin square, and then plug this into that. If you do all that, you can show that sin theta b is given by this equation here. If we choose mu2 by mu1 is equal to 1 now, then sin theta I tends to infinity, or there is no real theta I for making gamma perpendicular equal to 0. We don't see Brewster angle when it is perpendicular polarization if the medium is purely dielectric. There is no magnetic permeability there. If the material has different permeabilities, then yes, this will also show Brewster angle, but that is not of very great importance to us at the moment. So for the moment, for our discussions, we are looking at mu2 by mu1 equal to 1. Therefore, perpendicular polarization, there is no Brewster angle. If you plot the reflection transmission coefficient as a function of incident angle theta I for perpendicular polarization when the wave is incident from air to dielectric slab for two different values of permittivities epsilon r2 equal to 2 and 4, I get these two curves. Notice here the green trace corresponds to reflection coefficient and it will never go to 0. It starts from some finite value and monotonically increases and touches unity when theta I is equal to 90. Now, the transmission coefficient on the other hand starts from some other finite value and touches 0 when theta I is equal to 90. That means when theta I is equal to 90, the wave will not pass to the other side and everything gets reflected back. Looks logical, isn't it? Now, when the permittivity ratio or the discontinuity level increases, that is from air to higher dielectric constant, the reflection coefficient is generally higher. All these conclusions are very similar to that we saw in parallel polarization, except that in parallel polarization we had Brewster angle, whereas in perpendicular polarization for two dielectric interfaces, pure dielectric interface, there is no Brewster angle. Now let's look at this picture. We are going to now compare parallel and perpendicular polarization for a specific example when epsilon r1 is equal to 1 and epsilon r2 is equal to 4. Now we know that when the wave is perpendicularly polarized, there is no Brewster angle. The reflection coefficient is a monotonically increasing function of theta I. Whereas in case of parallel polarization, the red trace shows that the reflection coefficient first decreases at around 64 degrees or 63.4 degrees, it becomes 0 and then it starts increasing beyond that angle. So what does it mean physically? Look at the bottom picture here. We have a surface marked by a yellow line, and that's an interface between two regions, and there is a plane wave incident from the left side and it hits the surface, and this plane wave has the electric field which is arbitrarily polarized, which can be decomposed into a parallel component and a perpendicular component. The parallel components are indicated by blue arrows. The perpendicular component is indicated by crosses, indicating that the electric field is going into the plane of this paper, plane of this sheet or plane of the screen. Now, if this angle of incidence is equal to Brewster angle, then the reflected light will not have parallel polarization at all. That means the blue component will completely vanish and the reflected light only has perpendicular polarization. Such a light is known as polarized light. So, in case of reflection from glass, let us say, if the angle of incidence is such that it turns out to be equal to the Brewster angle, then the reflected light is polarized. And this has immense properties in real life. Let's take one example. Here we have two surfaces. Imagine that the top surface is a surface of glass, bottom is some board or something, some surface on which the glass plate is kept. Now the reflected light is polarized if it is getting reflected from the top end of the surface because it is glass. The bottom end of the light, bottom end of the surface, that is the green trace, whatever is reflected is arbitrarily polarized because that particular surface doesn't have the properties required to create the reflection coefficient which suppresses one component of polarization. Therefore, the angle of incidence for the top surface, top glass surface, is such that it is at the Brewster angle. Therefore, the reflected light is perpendicularly polarized. So, at the end of the thing, we are seeing two uh, images probably. One coming from the top surface, what we call colloquially reflection from the top surface of the glass, and other one from the bottom surface, what we call as the table on which the glass plate is kept. Now, if I were to put a device called a polarizer, Polarizer is a device which will allow only one particular polarization to pass through. It typically has thin molecules or wires which are very thin, closely spaced, parallel to each other. Therefore, only one component will pass through it. The component which is perpendicular to these lines will pass through it. At some point, we'll see, if we get chance, we'll learn about this polarizer. For this discussion, let's assume that there exists a device called a polarizer. The photograph is shown here. You can rotate this polarizer. That means you can decide whether you want the parallel polarization or perpendicular polarization to pass through it. You have a choice, let us say. Suppose if this device or this polarizer is oriented such that it blocks the perpendicular polarization. Say I have chosen that particular orientation. If that is the case, then what comes out of the polarizer will be only parallel polarization. Therefore, if I were to see the reflection through this polarizing lens, or polarizing film, what I see is only the parallel component, parallel polarized component. Since the top reflection from the top surface is perpendicularly polarized, that will not pass through the polarizer, but the reflection from the bottom surface will pass through the polarizer. That means if I were to see the reflection without a polarizer, I would see the top surface of the glass as well as the bottom surface of the glass or the top surface of the table on which the glass is kept. The moment I pass the reflected signal or reflected light through a polarizer which is properly oriented, then the reflection from the top can be completely removed. What I can see is only the bottom of the glass or the top of the table. So that is what we are going to see in the next video, where I'm going to show you what actually it looks in real life. All those equations, those ray diagrams, and the concept of Brewster angle and concept of parallel polarization, perpendicular polarization, everything can be combined into one video, which is this slide. If we can understand this and logically explain what is happening, probably we have understood the concept of Brewster angle. Let's look at the components, what's there in this video. This is a video, I'm going to play it in a moment, but let's understand the component first. There is a glass plate and you can see reflected light. Of course, there's a window there with some kind of curtain, so you can see the reflection of the curtain from that coming out of that glass plate. The reflection we are seeing from the top surface of the glass plate. And this plate is kept on a wooden board and I can't see the board at all. That means the light reflected from the surface is so strong that whatever is coming from the bottom of the board, I hardly can see it. This reflected light from the top surface is polarized, and the one from the bottom surface is not polarized. The top surface is polarized such that it has only a perpendicular component. The bottom surface has both parallel and perpendicular component. So far so good, we understand this. Now we have a polarizer kept here, and there is an person here who can rotate the polarizer, change the orientation of the polarizer. And there is a camera right behind the polarizer, and we are seeing the image here through that camera. That means what we are seeing here is what is coming through the polarizer. Since the polarizer is oriented such that it is allowing perpendicular component, we are able to see the reflection from the top surface, and if you can block it, then we can see the bottom surface also. We will see that. How do we see that? We rotate the polarizer. Rotate it such that we will orient it such that it blocks perpendicular polarization. Let us start the video and you will see the fun. Yep.
No, this is angle
So
is back.
the polarizer is being rotated here. A little noisy. When I took the video, I think there was a lot of noise in the lab. Now you can see that the bottom surface is visible. Can you see 4 holes here? Yes. Now again, she is continuing to rotate it.
Keep going.
Yeah, it will keep going. Keep watching what happens. I can see 4 holes there, which was not visible earlier.
No, this is
In
angle
fact, I
and
can see
line.
two holes. Other two holes are still. Third hole with difficulty I can
Keep
see.
going, keep going,
Fourth one
keep
is
going, keep going,
is just
keep
not
going.
there.
Stop.
Now you can see the fourth hole. Can you see that?
Leave it there.
Yep. Now the video is going to stop here, but what you observe here is the reflected light, which is polarized, has been completely blocked by the polarizer. The polarizer has been oriented such that we can see the bottom surface of the wooden board. Top surface of the wooden board. The wooden board has 4 holes here. I can see all the 4 holes here. For example, in this picture, it is the same thing. There are 4 holes. I hardly can see a hole. So if you are a photographer and you want to take a photograph through a glass and you are seeing reflections from the glass, and if you want to remove the reflection, all you have to do is find a orientation which corresponds to question quote unquote Brewster angle, and then you use a polarizer and remove the reflection. This works only from a particular angle. It doesn't work for all angles. It is important that reflected light coming from this surface onto the polarizer is coming at Brewster angle. That's very important, right? This has many more applications. This is a very powerful technique, powerful method. If time permits, if I get some get some opportunity, I'll show you some more uses of polarizing lens and the way Brewster angle comes into action.